So we have some time to work out the kinks. If you didn't have the opportunity to try it out or even to just create a voice thread, do take the time to do so. This is in part because the reason why I like to do this is to put faces with names. And also, sometimes people have different ways of saying their name than how I would say it. I don't want to screw up. Was a student last semester that I called her by the wrong name for 10 weeks of the semester, and I don't want to do that again. So, yes, so please take the time to do that. Just post one in that first homework assignment. I get updates whenever those roll in, so it gives me an opportunity to learn a little bit about each of you as well. Any questions about the homework assignment or voice thread itself right now? Yes, Kelly.
Do we all have to make a video?
Yeah, the way that it... Thanks for asking that. The way that I had envisioned this, and I probably should have explained it better, was that whoever created it first would create a video, share it with everybody else, and then the way that VoiceThread views things is you can upload individual videos from each additional person, and they're viewed as separate slides. So like as you're advancing from one to the next, you can view each as an individual video. Some people chose just to comment back on whoever posted the first video. That's fine too. I really didn't say which way you had to do it for this first one. Throughout the semester, there will be times where I'm going to ask you and a partner or you and a couple of partners to build something. For something like that, I want each of you to kind of create your own slide. Okay? And that's what I want to try to cover tomorrow, is how do you actually do that? And what's the difference between commenting back on somebody's versus creating your own slide? Thanks for asking that. Other questions? Okay. All right, one other thing I wanted to introduce you to real quick that I think I may have mentioned very briefly on Monday, but I anticipate the need for this is going to come up sooner rather than later. So there are a couple of ways you can communicate with me if you have questions. 1, just stop by my office. 2, shoot me an email. 3, up on Blackboard, I put this question and answer section, and what you're going to see, you may not be able to see all of these right now, but this is my view. So what you're going to see are individual forums for different parts of the course. So we're covering macromolecules. So if you've got questions that come up after lecture today or between on something that we covered that you just don't know the answer to, instead of emailing to me, what I'd like everybody to try and do is put it in here. I get an email right away because I subscribe to every one of these, and you can as well. But I subscribe to them, so I get an email anytime that a new question or new thread has been created in those individual discussion boards, and then I will just go ahead and respond. The benefit of doing it this way is that if somebody else in the class has the same question, I can address it one time instead of having to address it in 4 or 5 emails, which then saves me from being on my email all night like last night, which was okay. We watched the Good Place while I did that, so all right. All right, so those are a couple of things for housekeeping. For tomorrow, in lab, we're covering microscopy. So take the time to look over that ahead of time. And we'll do a little bit of staining as well. What today's focus in class is going to be our main thing is to get these 3 objectives. So describe properties of covalent bonds and hydrogen bonds. Describe pH, acid-base buffer with respect to hydrogen ion concentration, and then compare and contrast hydrophilic and hydrophobic molecules, which was in part what I asked you to do to prep for today. What are some properties of these? Okay. Rather than all of us kind of going through and saying, how did we respond to that, keep in your mind what you said. Actually, let's do this. Write down on a sheet of paper, it can be the one I handed out, can be one other. Just write down real quickly a summary of what you said. What are some properties of hydrophilic and hydrophobic molecules? We're going to use this as the basis for most of today's discussion. All right, before we get there though, let's cover some very basic chemistry. Bonding. Primarily what we talk about in here are covalent and hydrogen bonds. Those seem to be the most important, not only for creating macromolecules, but also contribute to the three-dimensional structure of many of the molecules that we talk about throughout the semester. Okay? 4 main atoms that we will see in micro, because these are primarily the ones that are the basis for life. Carbon, hydrogen, oxygen, nitrogen. Phosphate to some extent, but we're not going to worry as much about that one right now. One thing that I want to make sure that we have straight right away is how many electrons are in each of these, how many electrons are in the valence shell, and how many bonds can each of these form. Okay? So for example, hydrogen has 1 electron. Maximally in its valence shell, it can only hold 2. Therefore, it's got 1 free spot for an extra bond. Okay. Anybody recall how many electrons carbon has? It has 6 total, but how many in the valence shell? Just 4, right? Maximum in its valence shell? 8. Therefore, it can form how many bonds? 4 more. And that can be a combination of 4 single bonds, 2 double bonds, a triple bond and a single bond, 2 singles and a double. Anything that adds up to a total of 4 bonds. Okay? To finish this out, oxygen has 6, nitrogen has 5. Tell me how many bonds each of these can form. And I already heard somebody say it. So for oxygen, 2, Annie, nitrogen, 3. Okay. We'll come back to this. This is important because a lot of the molecules that we're going to be looking at use these, and I want to just make sure that we're kind of straight on how these molecules look, but also how the electron configuration can contribute to the bonding for each of them as well. All right, let's get into hydrophilic and hydrophobic molecules. The way that I was thinking about this last night about how do I want to approach this, and my first thought was let's concept map, and then I was like it doesn't work for this one. I tried it and it doesn't work. So I created this worksheet, this table here for us to kind of walk through the process. And really what we're trying to understand today is how do the properties of the bonds, polar and nonpolar bonds, how do those contribute to properties of being hydrophilic or being hydrophobic? So we're going to kind of take a stepwise approach to addressing this. Okay, I'm not going to go off the slides for most of today. Okay, those are there for you to review. I may jump to them occasionally as a way for us to kind of reiterate a couple of points, but I'm going to kind of chalk talk this for most of the time. All right, so let's just start with the first. There we go. Okay, so polar, nonpolar. What does it mean that a bond is polar? What are some basic characteristics? Perfect. Let's start with that because that's the first one on the list, right? So these bonds have atoms that have a difference or a similarity in an electronegativity, right? What is electronegativity? What does that term actually mean? If you could describe it in your own terminology. Okay. Anybody seen a tug of war before? I'm sure most everybody has seen tug of war. Okay. What is the purpose of tug of war? Or how do you win the game? Nancy?
Like pulling.
You're pulling, right?
So electronegativity pulls electrons from other atoms.
Beautiful. Beautiful. Pulls electrons from other atoms. Okay? Carbon, hydrogen, oxygen, nitrogen, they each have a certain electronegativity value. I'm not asking you to memorize them. I will give you those values on any single exam or anything that you need the information for. But the basic premise of electronegativity is that when two atoms are involved in a covalent bond, they have a certain pull or affinity for the electrons that are within that bond. If two atoms have similar electronegativities, it means that the electrons are pretty much equally shared between the two. But if one is much stronger than the other, okay, so if I'm to go up against Dwayne "The Rock" Johnson in a battle of brawn, he is much more electronegative than I am. Okay, he will be able to pull those electrons towards him, making him more electronegative, me more electropositive. Okay, or partially negative and partially positive would be the terms that we use. So a way to model this: hydrogen, oxygen. Hydrogen has an electronegativity value of 2.1. Oxygen, on the other hand, has an electronegativity of 3.5. Which is more electronegative? Oxygen is. Therefore, in a covalent bond between these two atoms, what we're going to find is that the electrons are going to be pulled in the direction of the oxygen. Okay? If we're thinking about how does this look with electrons or their movement, one of the ways we can draw this is the electrons more often are going to be found closer to the oxygen than they are the hydrogen. What else are common parts of an atom? We've got electrons. What's in the middle? What's in the middle? Protons and neutrons. What's the charge on a proton? Positive. Neutron? Nothing. Neutron. So what we find is that as the electrons are being pulled away from hydrogen in this case, we think of it as like unshielding. The electron that's around it, which is a negative charge to the positive charge of the proton in the middle of hydrogen, since it's being pulled away, it increases kind of this force of the positive charge from hydrogen's nucleus. And so what we find is that that hydrogen begins to carry what we call a partial positive charge. We can signify that with this delta positive symbol. Oxygen, on the other hand, now has electrons, more electrons closer to it than it does have protons. It carries a partial negative charge. What kind of bond is this? Ones that have differences in electronegativity. Are these polar or non-polar? These are our polar. So if we look at the table here, the first answer to that question, bonds that have, so polar bonds have atoms that have quite different electronegativity values. The number that we use, if the difference in electronegativity is equal or greater than 0.5, we consider the bond to be polar. Nonpolar bonds have electronegativities between the two atoms that are similar. In those cases, the difference in electronegativity is less than 0.5. Let's look at a couple of examples. Hydrogen, nitrogen, oxygen, carbon. I'll list the electronegativity values. And I'll give 3 different bonds. You tell me mentally, telepathically, polar or nonpolar. Okay, I'll give you a minute. All right, hydrogen, nitrogen. Polar, nonpolar?
Polar.
Polar. Difference is greater than 0.5. Which one carries a partial negative charge? Nitrogen does. More electronegative than the hydrogen is. Okay. Oxygen, carbon. Polar. Partial negative would be on the oxygen in this case. And then how about carbon, hydrogen? Nonpolar. Difference is less than 0.5. Okay. What are hydrophobic molecules typically made out of? Nonpolar bonds. What's an example? Ah, that's a good one. Hydrocarbons. What is a hydrocarbon? We'll come back to that, okay? We'll make sure that we cover it either later today or on Friday. All right, so if you're kind of following along with the table, what we've got so far, we've answered the first one. Second box or row, electronegativity difference contributes to, and the term here should be equal or unequal sharing of electrons. So in polar bonds, we have unequal sharing of electrons. In nonpolar bonds, we have an equal sharing of those electrons between the two atoms, or between the two atoms involved in the bond. And then row 3, the atoms in these bonds, we would say for polar bonds, they carry a partial positive or a partial negative charge. Again, we use that Greek symbol delta. Or in the case of nonpolar, they carry no charge. You could just put no charge, I suppose, would be the best way to describe it. Okay. Let's move to the next part. Water. Okay. Water has 2 oxygen-hydrogen bonds. We've defined those already as both being polar. We've defined that as oxygen will have partial negative charges. Hydrogen atoms here will have partial positive charges as those electrons are being pulled towards the oxygen. Okay. Why is water able to dissolve substances? Why is water able to dissolve, for example, glucose, table sugar? What's the property that we see here? Hydrogen bonds are a result of the electronegativity. Water is a polar molecule, right? And polar molecules, like water, we say that some, not all, can be dissolved in water. But dissolving a substance is based on the ability to form what we call hydrogen bonds. What is a hydrogen bond? It's at least a bond involving what? Hydrogen, okay? But it only involves hydrogens that have partial charges associated with them. So water is an amazingly good solvent because it can dissolve substances that, like it, are polar. Okay? So for example, if we have any old molecule, we'll just call it R right now. And let's say R has a carbon-oxygen bond on it. We know that oxygen is partially negative. We know the carbon is partially positive. If you have a magnet, or two magnets, what attracts? What interaction do you have to have between two magnets in order for them to clink together? Opposites attract. Okay. A positive and a negative charge in a magnet. And there's some analogy here. What we're looking for is partial positives to interact with partial negatives. What we get is an electrostatic interaction, or something that's kind of like a magnet, where the partial charge on the hydrogens will interact with the partial negative charge on the oxygen with this other molecule. And if we get enough water molecules surrounding this atom here, or this molecule here, what we get is that molecule being dissolved. Okay, I liken it to Harry Potter. All right, cloaking devices. So in Harry Potter, he throws out in the first movie, he gets a cloaking device for Christmas, right? One of those nice, whatever. Sorry. Anyway, he can be hidden in plain sight, right? By being shielded by this cloak that he wears, an invisibility cloak. That's the word I'm looking for. And that's exactly what happens when a molecule becomes dissolved. It basically becomes invisible behind a shield of water. Okay? Sometimes it's called a hydration shell. We can also see these types of interactions occurring not only with hydrogen from water, but vice versa. So in this molecule here, we've got a carbon with a partial positive charge. What is that going to interact with on a molecule of water? It'll interact with the partial negative charge of oxygen. And so we can see the opposite effect as well, where it's the partial negative charge of the water that's interacting with a partial positive charge on whatever molecule is being dissolved. Okay? So polar molecules, ones that can typically be dissolved, something that's dissolved is described as what? Hydrophilic, as opposed to nonpolar molecules, which are hydrophobic. Okay? There are exceptions to this. Not every single hydrophilic molecule can be dissolved. Okay? The example I give every single semester, how many individuals have taken a shower in the past 48 hours? Good. Okay. How many of those individuals dried off with a towel? Still good. Okay. What's a towel made of? What's cotton made of? What kind of macromolecule is it? Is it a... It is a hydrophilic one, that's true. Carbohydrate, protein, lipid, or nucleic acid. What is cotton? It's a fiber, right? And something fibrous like that, that's a carbohydrate. So carbohydrates like sugar, like cotton, incredibly hydrophilic. And yet, thank the Lord, our cotton towels don't dissolve, right? Why not? Why, even though it's hydrophilic, why can't it be dissolved? Simple answer, it's too big. Not the towel itself, but the cotton fibers itself are too large to actually be cloaked or made invisible by the water molecules that are interacting with it. Okay. Other examples of this would include things like starch, or even like if you play with the strings on celery, those are starch-based, cellulose-based molecules. Those are carbohydrates. Those don't dissolve in water either. Okay. So because a molecule is hydrophilic doesn't necessarily mean that it's going to dissolve. All right, so going back to the chart real quick, because of the difference in electronegativity and charge, we can find that molecules that are polar may have some full charges in case they're involved in ionic bonding as well. These atoms can be involved in hydrogen bonding for polar. Ones that are not polar, because they don't carry any charge at all, not even partial charges, typically we say that they are not able or cannot be involved in hydrogen bonding. We've addressed the one afterwards. We've said polar molecules are typically hydrophilic. Nonpolar molecules are hydrophobic. And then for the one after that, polar molecules may be dissolved. And the reason why I put may here, it's a hesitant term, but that's because there are exceptions. Okay? So they may be dissolved. Hydrophobic ones, typically we think of as not being able to be dissolved. So what are some examples? What are some examples of hydrophilic and hydrophobic molecules beyond the ones that we've already brought up? So, no cotton towel is an example. Take a minute. Write down a couple for yourself. Use the table here to guide you. What are examples, maybe even in everyday life, that are examples of hydrophilic or hydrophobic molecules? Anybody got a good example? Doesn't have to be a good example. Anybody have an example, period? Morgan?
Like water for nonpolar?
Water is absolutely nonpolar.
I'm sorry, oil.
Oil. Thank you. Yes. Oil is absolutely nonpolar. So, anybody have a salad in the past week and a half that involved vinaigrette? Right, you take vinegar and oil, mix them together, the two of them will separate because the oil being nonpolar, we find nonpolar interactions driving them to congregate together, and then the vinegar itself, being polar, could dissolve anything else, but will typically form hydrogen bonds with acetic acid, which is vinegar, rather than with the oil. What else?
Butter?
Oh, who said butter? Thank you, Kelly. All right, butter is
Nonpolar?
nonpolar and wholly delicious. Annie?
Salt?
Salt. What would you put that one under?
Polar.
Polar, yeah. It at least can be dissolved, right? It carry, in comparison to some of these other ones, it doesn't have a covalent bond in the same way, right? So salt would be one. It would be molecule or chemicals that have full positive or full negative charges, right? So there's a little bit difference there, but still they can be dissolved. Right? They're still hydrophilic. Okay, and there's many others, and we'll kind of go through this over the next couple of class periods. But the reason to bring this up is because this balance between hydrophilic and hydrophobic, it creates boundaries. And what I mean by that is, for example, think of a cell. What makes the outside of a typical, when you imagine a eukaryotic cell? What is the outermost part? What do we call that? A cell membrane. And what's a membrane made of?
Lipid bilayer.
A lipid bilayer, a phospholipid, and we'll talk about some more on Friday. But that contains a hydrophilic head, but two hydrophobic tails. And those hydrophobic tails create a boundary. All right, they create a physical boundary that separates what's happening outside of the cell from what's happening inside of the cell. And it contributes to homeostasis. So the balance here of hydrophilic and hydrophobic, and in understanding some of the basic principles of it, is really important to understanding cell physiology. That's the purpose. Okay. All right. Any questions on what we've talked about so far? All right. Here's what I want to do. Take another 2 minutes. Look at your original answer that you wrote down. Properties of hydrophilic and hydrophobic molecules. Okay. What I want to do is two parts to this. First one is take a look and then determine, are there particular weaknesses in your answer? Or were you incorrect on something? And if so, make those corrections. If you've got a good answer and you think it's great, move on to part 2, which is compare and contrast hydrophilic and hydrophobic. So write down some similarities and or differences between hydrophilic and hydrophobic molecules. I'll give you 2 minutes. Where are examples of where this could be found in a prokaryotic cell? Question?
So when I tried looking at
Yeah.
the lesson yesterday,
Yeah.
the pictures wouldn't come up.
Damn it, I've worked so hard to try to get this to work. Okay,
It says like error or something.
damn it!
Yeah, it's like not.
It's like the same issues as last semester. I worked my ass off to get this to work. Okay,
So people can take a picture.
I will, you know what I'll do is I'm going to just create a hyperlink for each of these pictures so that you can click on it and it shows you what it is.
Okay.
That'll make life easy. But each group member, I rearranged a couple of the groups because somebody who I don't think even showed up on Monday dropped the class, so it took one of our groups down to 2. I just took those 2 individuals and put them into new groups. So now every single group has 4 individuals in it. Each person should take one of these molecules and fill in a complete row. Okay? You can decide among yourself who will do what, but what I want you to do is put your name in parentheses somewhere in your row so that I can see everybody has done this. Okay? And this is what we'll begin with on Friday. So I'll go back to my office, I'll work on this for a little bit, but otherwise, yeah. All right, you can leave 4 minutes early. I'll see you later. Have a great rest of the day.